So just to give a recap of where we got to on Monday, what we're interested in on Monday was trying to get estimates of the survivor function. So the estimate that, an estimate for the probability that a particular individual or object or item will last longer than a particular time. And in the case where we know exactly when at least some people fail and when some people are censored, then we talked about that we were going to try and do that by something called a Kaplan-Meier estimate. Okay, so here is my illustration of my plot of my trial. 0 is when everybody starts, so it's relative to them, and then time kind of progresses, and then the separate times when individuals are seen to fail, I've ordered, and so at the first failure time, I see D1 failures. Okay, so D1 could be 1, but it could have 3 people fail at the same time, or 2, or 10. Then, sorry, this should be T2, should be the second time when D2 people fail. Then at the F's distinct failure time, I have DS people fail. And as well as that, I have some people who are right-censored. So all I know is that in the interval between 0 and T1, I lose contact with I1 people, and they basically haven't failed yet. So we know that these individuals last longer than the point when they were censored. Okay, so that's the kind of data that we had, and we basically kind of said to get an estimate of the survivor function. So the probability that somebody lasts at least till time t, we want to take account of the censorings as well. And what we're going to work out is we're going to work out a product term, and we're going to consider basically, if I'm interested in a time t that is between the F's failure time and the S plus 1 failure time, then I'm going to consider each of these points beforehand, and at each of those points beforehand, I'm going to multiply together the number of deaths, or 1, minus the number of deaths over the number of people who are at risk. So the number of people at risk was adjusted to take account of the people who were censored. Okay, so that's kind of what we did last time around. So at time T1, for example, I started with N people. I lost contact with I1 people before they'd failed and before this time here. So the number at risk here would be N minus I1. The number at risk here, well, I'd lost I1 people, then D1 people actually failed, and then I lost contact with I2 people. So here the number at risk would be N minus I1 minus D1 minus I2. Okay, so each particular distinct failure time, we're going to work out the number at risk. We're going to work out the number of people who died, and then to get our estimate of my survivor function, I'm going to just multiply them together, and I'm going to get a plot that looks... Oh, have I got a plot of it? No, which way do we go? Basically, it kind of has jumps down. So it's constant, and then each time we actually observe a failure, it will kind of drop down. Okay, does everyone remember that from last time around, or rough recap? Good. Right, so at the end of last week, we actually did a particular example. And the particular example that we had was an example that considered people who had a tumour, and they'd come into a hospital. They had been given some treatment, and their tumour had sort of had been taken out. And then we're interested in the time it takes until their tumour comes back again. So that's called a relapse time. And what happens is that 6 people relapse. So the first person relapses at 3 months, and then there's 2 people who relapse at 6.5. So according to my plot, so this is going to be relapses and the kind of number of them. It's 2 people relapse at 6.5 months. 1 person relapses at 10 months. 1 person relapses at 12 months. And 1 person relapses at 15 months. Okay, so they're the people that I actually observed to fail. And then there's some censoring going on as well that I need to take account of to get to do reliable estimation. So 1 person I lose contact with at 8.4 months, and their tumour hasn't come back yet. So basically, there's somebody who's censored. At 8.5 months, there's another person who's censored at 4 months. There's another person who's censored at 5.7 months. And there's another person who's censored at 10.1 months. Okay, so I can draw that picture, and then last time we worked out by hand what the survivor function is. Okay, now in this example there's only sort of 10 people. It's relatively easy to work out my survivor function. However, typically you're not going to want to do it by hand. You'd like your computer to do it for you instead. So nicely in R, people have written a big library, and this is what we get for the survivor function if we work it out. So people have written a library that everybody is freely accessible, that includes all of the survival analysis sort of functions that you might ever want to kind of implement. So let's see how we can actually kind of now implement this, working out this Kaplan-Meier estimate in R rather than having to do it by hand. Okay, is that big enough for people to see? Yeah. Okay, so the library is called survival. So you need to start off by loading that particular kind of like library and potentially kind of installing it if you don't have it. Okay, and then I've saved the data in something called tumour. Okay, so tumour is seen down here. It basically consists of 2 vectors. So I need to put into R 1 vector which just consists of all of the times. So I have 2 variables. Okay, so 1 is basically that x that I talked about at the start, which is xi. And it's the times that things happened. So either the time that they failed or the time that they were censored. Okay, and then censoring is telling you whether that person failed or not. So xi is the times that things happened. And censor, in this case, is my delta I. And delta I is equal to 1 if they actually failed. In this case, that's a relapse. Or 0 if they were censored. Okay, and they sort of need to be in the same sort of order. So time 3 and censoring 1 means that we observed a relapse at time 3. Okay, time 4 and censoring 0, that corresponds to the person who was censored at 4 months. 5.7, that's a censoring, so we know that that person hadn't relapsed by 5.7 months. And this person here is the person who relapsed at 12 months. Okay, so we're going to kind of create some data in 2 vectors like that. And then the first thing we need to do in my survival analysis library is try and link together the times and the censoring to create what's called a survival object. Okay, so we've got a vector time, we've got a vector sensor. this command here, serve time sensor type equals right, tells the computer that you want to link those together, and the people who are censored, so the people with 0, have right censoring. Okay, so that's the first thing that we have to do. We have to tell the computer that it should link together the time and the censoring vector, and that the type of censoring that I have here is right censoring. So I knew that people relapsed after a time, but not exactly when. Okay, so that's created that object, and then all you have to do to get your computer to create a Kaplan-Meier estimate is use something called servFit. So servFit is a function. On the left-hand side, you put in the survival object that you've created, and then like a linear model, you put a tilde that tells you kind of how you want to split up the right-hand side. So in this case, we just think it's a single group. So we just want to create one survival object, one Kaplan-Meier estimate for everything. So that's what that command does. And then that will work out my Kaplan-Meier estimate. And if I run a summary, it tells me, it's going to work. Ooh. Let's try running it again. It basically provides me in the computer exactly the table that we worked out last time around. Okay, so these are the particular kind of like times that my failures were. This is the number of people who are at risk just before each of those failures. These are the number of people who failed. And that's my estimate of what I think the survival function is at each particular kind of like time. As well as that, it gives me an estimate of what I think the standard error is on this survival estimate, and a lower and an upper 95% confidence interval. Okay, so if I want to, say if I want to work out an estimate for the survival time between time 3 and 6.5, then that will be 0.9. If I was interested in what an estimate for my survival was at time 11 months, I would look to the 10 that's above it, and I get 0.482. Okay, so it can give you a summary like that. You can also plot it. Okay, and it will give you a sort of a plot of what it thinks the survival function as well, complete with confidence intervals. Okay, so again, if I basically want to work out an estimate for what's the probability that somebody will survive longer than 9 months, I'd read up to there, and I'd presumably get something about 0.75 or something like that. Okay, so R can basically work all that out for you, as well as kind of giving you point estimates. It can give you confidence intervals and standard errors on the estimates at any particular point as well. Okay, any questions about that?
What's the meaning of the dashed line?
So the dashed line, they're the confidence intervals. So this is the lower 95% confidence interval, and this is the upper 95% confidence interval for the survivor function. So just to summarize then, we've got two methods of initially kind of like trying to do an exploration of what a survivor function is given some data. We talked about live tables, and for live tables is generally kind of where the observed data is going to be grouped into intervals. So you don't know exactly failure times, you just know the number of people who failed within a particular kind of like year. And when you have censoring there, what we're going to try and do is we're just going to adjust the number at risk for each particular year for the people who are censored. Okay. If the observed failure times are exact, then we can do better than life tables by doing this Kaplan-Meier estimate. And what we're going to try and do is we're going to multiply together 1 minus dj over rj terms, where we sort people into their orderings of failures. dj are the number of people who failed at each time, and rj is the number of people who are at risk, and that's the bit that we adjust for the censorings. Okay. So yeah, we basically, if we have censored data, then we need to basically take it into account properly. So we need to do one of these two particular kind of like methods. We can't just kind of like draw a histogram because we don't know where to put the censored observations. Okay, and I would suggest very, very, very strongly that whenever you observe some data that is of survival analysis form, that the first thing you should always do is plot one of those things. So typically now it's quite common that you do get exact failure times. So people do Kaplan-Meier estimates a lot. They are basically the first thing that you should do when you kind of collect data. And the reason that they're the first thing is of what you should do is that they will help you decide how you might do a more complicated analysis afterwards. Okay, so you plot your Kaplan-Meier estimate, and that will kind of tell you what it thinks the survival function is, and that might tell you, well, do I think I can now model the failure times by a particular distribution, or am I going to have to kind of keep things as being a non-parametric, so not pick a particular kind of like distribution to model my data with. But yeah, always make sure you do a Kaplan-Meier plot before you kind of like start off. Okay, so both of those Kaplan-Meier and life tables were what's called non-parametric. So statistics, I'm not sure how much of this kind of you've already kind of done non-parametric and parametric stuff, but statistics sort of splits up into two different groups. So you can either take a non-parametric approach or a parametric approach. So non-parametric is where you've observed some data, but you really aren't very sure what distribution it comes from, and you don't want to make a particular assumption about the form of that distribution. So for example, you collect some data and you go, I'm not convinced that that data, it comes from a normal distribution, for example, or an exponential, or anything that I particularly kind of know about. I'm going to try and analyze it without having to make that assumption that it arises from a particular family of distributions that's called a parametric family. Okay, so that's what we did with life tables and Kaplan-Meier. We didn't assume that the data were exponential or Weibull or anything like that. Okay, so that's a non-parametric approach. A parametric approach is that we're going to assume that my failure time comes from a particular family of distributions. Okay, and that's probably typically what you have done so far in sort of your stats sort of career. You've observed some data and you assume that it came from a particular family of distributions. So it came from a normal distribution, and then you're trying to fit the parameters of a normal to the data you've seen. Or a binomial distribution, you're trying to estimate p. Or an exponential, and you're trying to estimate the rate. So that's a parametric approach, that we're going to assume that failure time, in this case, comes from a particular family of distributions. And that family of distributions is parameterized by theta. So exponential is parameterized by the rate. Weibull is parameterized by two parameters. Okay, for a parametric approach, then all we need to do to specify our distribution is try and work out what theta is. If we can work out what theta is, then that will tell me everything I need to know about that particular distribution. Okay, so there are two approaches in statistics in general, non-parametric or parametric, and there are two approaches in survival analysis, and we're going to try and do both of them. So throughout the course, we're going to explain, well, if you don't want to make an assumption about the form of the failure time, so if you want to be non-parametric, this is what you do. If you are happy making an assumption about the form of the distribution of the failure time, you can be parametric, and this is the analysis you should take. Okay? And part of the key reason that you should do a Kaplan-Meier estimate first is it might tell you if the survival time looks like a model that you know about. So if you plot your Kaplan-Meier estimate and it looks like it has exponential decay, or reasonably like it has exponential decay, then that would potentially fit with t coming from an exponential distribution, and then you might kind of say, oh, I can now do a parametric analysis. And I'll assume that t comes from an exponential distribution, and I can do all of those tools that I get from that. Whereas if I plot my Kaplan-Meier estimate and it looks really crazy, doesn't look anything like an exponential distribution, I'm going to have to stick probably with my non-parametric approach. Okay, so both of these approaches have some advantages and disadvantages. So basically, I would say, if you can choose the right distribution, so if you actually model t with its true distribution, then a parametric approach is much more powerful. It'll give you much kind of more accurate answers. Okay, so if you're going to model t by an exponential distribution, and t really is quite close to being an exponential random variable, then parametric could be the way to go. Okay, but if you model t by something which is actually nothing like whatsoever, then you're going to get really bad answers. So if you model t incorrectly and take a parametric approach, you're going to get bad answers, whereas if you with a non-parametric approach, you'll still get good answers, but they just might not be quite as powerful as they could be. Okay? So both of them have got advantages and disadvantages. It basically depends upon whether you can pick the right distribution to fit for t for if you're going to go for the parametric approach. Okay, so Kaplan-Meier was the non-parametric approach. What we're going to do if actually we decide that we want to take a parametric approach, how can we create an estimate of the survivor function in that case? And what we've always done whenever we've taken a parametric approach to statistics is we've always used the maximum likelihood estimate. So we're going to use the same idea for survival analysis, but we're just going to have to take into account the fact we've got some censorings when I'm going to do my maximum likelihood estimate. Okay, so if we were going to assume a model that my t's came from an exponential distribution with rate lambda, so for example we might have plotted at the start my Kaplan-Meier estimate, okay, and it looks roughly like it exhibits exponential decay. Okay, then potentially that would fit with the data coming from an exponential distribution. Okay, so we might do this Kaplan-Meier plot first. We might get a plot that looks like it has exponential decay, and then we might decide, right, I'm going to model my failure times by an exponential distribution. How can I estimate lambda? Okay, well, I said all we're going to do is maximum likelihood, and we all hopefully know how to do maximum likelihood. So if we didn't have any censorings whatsoever, then we're going to observe a whole load of times, t1, t2, t3 up to tn, that come from an exponential with rate lambda. If I want to work out my likelihood for lambda given those particular failure times, all I'm going to do is I'm going to take my PDF, because there's no censoring, and I'm going to multiply them all together. That gives me this thing here. If I kind of multiply together all of the f's, then I'm going to do my standard trick of saying, well, it's a bit hard to maximize my likelihood, So I'm going to work out the log likelihood, because that will turn my product into a sum. So work out my log likelihood, and then I'm going to differentiate it, set it equal to 0, and that's going to be my MLE. Okay, that's just my standard MLE approach. And I can certainly do that if I don't have any censorings, because if I don't have any censorings, then the times that I see are just going to be my exponential random variables. Okay, and if we observe a whole load of exponentials, then the lambda hat we get is n, so the number of individuals divided by the sum of all of their failure times. Okay, so we can go a little bit further than that as well. I'm not really going to go into it here. Don't need to worry about this too much. But as well as just having a point estimate for lambda, then we can also try and kind of work out a confidence interval for lambda using some properties of random variables. Okay, you don't need to kind of worry too much kind of about those particular formulas. Just can be happy that you can work out a confidence interval. So you can get a point estimate and you can work out a confidence interval. Okay, but that's only true when we don't have any censoring sort of whatsoever. But we are going to have some censoring, so we are going to have to slightly alter that later on. Okay, we've got a point estimate, we've got confidence intervals. If we're interested in trying to find out about other parameters, then we also, as we learnt in sort of second year analysis, that the MLE is kind of invariant. Okay, so whether you maximize lambda or you maximize 1 over lambda and fiddle around with it, you kind of really get the same answer. So you kind of have this sort of invariance. So if you want to work out an MLE for any other parameter that's basically a function of the theta, all you have to do is plug in the MLE of theta into your kind of other thing. Okay, so for example, if we want to get a plug-in estimate for the survivor function at a particular kind of time t, then our formula for how to get from my lambda to the survivor function is s of t is equal to e to the minus lambda t. So if I want an MLE estimate of my s hat of t, all I have to do is plug in my MLE for lambda. So I just have to plug in lambda hat into that formula up there. Okay. Equally, if we want to find an MLE for the median survival time, so that's the probability, that's the time where there's a 50% chance that someone will last longer than it and a 50% chance that someone won't last as long as it, then we want to find the value t tilde where the probability that someone will last longer than t tilde is a half. Okay, so we've got my formula for s of t. We can like plug that in, fiddle around with it a little bit, sort of invert it to get t tilde in terms of lambda and a half. And then if I want my MLE for t tilde, I'm just going to plug in my lambda hat. Okay, so that's just sort of the invariance of the MLE. Once I've got my MLE, I can plug that number in to get me MLE estimates of other things that I might like. Oh. Okay, so that hopefully should just be a recap of MLEs that we've kind of done in the past. Now we're going to use the same idea for survival analysis, but what we're going to have to try and do is we're going to try and modify the likelihood a little bit to take account of the fact that we now have some right censoring. Okay, so we're going to do the same idea of trying to write down the likelihood as a function of lambda, take log of it, differentiate it and set it equal to 0 to work out the maximum. But what we are going to have to do is we're going to have to try and alter the likelihood that I'm going to work out to take account of the fact that I have censoring. What have I done with? Okay, so with survival analysis kind of set up, if we assume we've got right censoring for some of the individuals, then our model is that all of my failure times are going to be exponential with rate lambda, but I haven't seen all of my exact failure times. So for some people, I've seen their exact failure time, but for some people, all I know is their failure time is bigger than a particular time. Okay, so I guess how can I kind of like write this down? So I've got individual I've got their sort of event time, and then I've got their contribution to the likelihood. Actually, let's put a so delta I is a failure indicator, and then I've got my contribution to the likelihood. Okay, so let's assume that maybe I've got sort of n individuals. Okay, individual 1, maybe I assumed that what I observed was T1, and basically for that person, I actually observed their failure. Okay, for person 2, I observed that person was censored. So all I know is that that person lasted longer than a particular time C2. So their failure indicator is going to be kind of like 0. Maybe this person here failed, and I'm going to see them, and this person here, maybe CN. Okay, so they're a censoring like that. Okay. Right, so now we're going to think about what contribution to the likelihood each of these people kind of like added. So in particular, we're going to note that for T, which is distributed exponentially with rate lambda, then my density at a particular time t is lambda e to the minus lambda t, and the probability that t is bigger than a particular time is e to the minus lambda t. Okay, so individual 1, we saw fail exactly. Okay, so their contribution to the likelihood is going to be kind of the density at the point that they failed. So this person's contribution to the likelihood is going to be f of t1. Okay, observe that person kind of fail exactly. Okay, this person here, okay, we didn't observe fail exactly. All we know is that this person here lasted longer than time c2 star. So if we're going to work out their contribution to the likelihood, their contribution to the likelihood is kind of going to be the probability that t is longer than c2 star. So this person here is going to have, I should have written this bigger, hopefully you'll be able to fit that in. So that's going to be that person's contribution to the likelihood. This person here, they failed, so what's their contribution to the likelihood going to be? Yeah. Okay, and then this person at the end, they were censored, so what's their contribution to the likelihood going to be? Is it going to be an F or is it going to be a P? Yeah. Okay, and then to work out the main likelihood, we're just going to multiply all these terms together in exactly the same way as we do for a normal likelihood. Okay, so the only difference is for the people who are censored, their contribution to the likelihood is going to be these terms here rather than the individual densities. Okay, and we can sort of put all of that together. Okay, so sort of when we have failure times that we're going to model with an exponential with rate lambda, okay, and some of the observations are censored, then if we want to work out the likelihood of lambda, what we're going to do is we're going to split it up into two parts. We're going to work out what's the contribution to the likelihood of the actual observed failures, and we're going to multiply that by the contribution to the likelihood of the censorings. Okay, so all of the people who we've observed to fail, we're going to multiply together, and they're all the people with delta I is equal to 1. Okay, so they're all the people who have an indicator function for failure is equal to 1, and their contribution is just going to be the density of their particular failure times. And the contribution to the likelihood of the censorings, well, they're going to be all the people with delta I is equal to 0, and their contribution is going to be, well, what's the probability that you would, for them, their t would be bigger than their censoring time. Okay, so just to make it a little bit easier to sort of work with, we can try and write it now from I is equal to 1 to n as a product from I is equal to 1 to n, and that's f of ti to the delta I times the probability that t is bigger than ci to the 1 minus delta I. Okay, hopefully you can see that these two things are the same. So this is a product of lots of terms. If delta I is equal to 1, the bit that's going to be there, and this is not going to be there. If delta I is equal to 0, that's going to be there, that's not going to be there. So that's the same here. We're kind of cycling through all of the individuals. If delta I is equal to 1, their contribution is going to be f. And if delta I is equal to 0, their contribution is going to be this. Okay? So those two things are sort of the same. And hopefully it kind of makes sense from kind of this thing up there as well. Okay. And then all we're going to do is we're going to try and plug in. Let's write it up here. Oh, sorry. We're going to plug in those things there into there. So I'm going to get my likelihood for lambda being equal to the product from I is equal to 1 up to n of lambda e to the minus lambda ti to the delta I times e to the minus lambda ci to the 1 minus delta I. Okay. We work this out. A little bit of algebra that I don't want to do on the board. Take logs. And maximise by differentiating and setting it equal to 0. Then what we eventually work out to be is lambda hat is the sum of the delta i's divided by the sum of ti delta I plus ci 1 minus delta I. Okay, and that actually kind of has a really kind of simple form to sort of remember. So on the top, my delta I is just the number of actual failures that I observe. Okay, and my number on the bottom is basically just the length of time that I actually observe everybody for. Okay, so for the people who failed, I observe them until they fail, so that's ti, and for the people who are censored, I observe them until they're censored. So the bit on the bottom is the total time that people are observed while they're alive. Or observed alive. Okay, so it has quite a simple form to sort of remember. Okay, and that's really all I've written down here. So delta I is the total number of failures that you've actually seen, and the bit on the bottom is the total time alive that you've observed all of the patients. So for the individual, you add the failure times of the people who failed, and you add in the times until you lost contact or the people who are censored were censored. And then your lambda hat is just 1 divided by the other. Just like before, you can try and work out asymptotically what the variance of lambda hat is. And you find that a variance of lambda hat is approximately your lambda hat squared divided by the number of failures that you see. And so if you want to get a confidence interval, then you do your standard thing of taking your lambda hat and you add or subtract your 1.96 times the square root of kind of your standard error, so the square root of this thing here. Okay, so we can get a value of lambda hat, we can get a confidence interval for lambda hat as well. Finally, if we're kind of interested in other things, then we can use the plug-in principle to try and find a point estimate. If we want to find out confidence intervals for the other things, we can use another result that came from sort of second year statistics, that if I have a function of a random variable, I can approximate the variance of that new random variable by working out this thing here. And so, for example, for an exponential, lambda is my rate. If I want to instead work out 1 over lambda, well, that's the expected failure length until somebody kind of like fails. So that's mu hat. To work out a point estimate, I work out 1 over lambda hat. To work out a variance for mu hat, I use this particular thing here. And working it through, I work out my mu hat squared and then divide it by the sum of my delta i's. So I can get confidence intervals for mu hat, or the expected length of time until somebody survives as well. Okay, so that's everything I think for today. Next week we'll work through an example and then we'll start talking about how we can actually compare two different groups. So this has all been talking about, we've just got one group, what can we find out about one group? Next week we're going to start talking about probably the more interesting question of saying, now I've got two different drugs that I'm giving people, can I tell if one drug is better than the other drug?